Hello everyone and welcome back to Indian Genes. Also a huge welcome to our listeners who are tuning in for the first time today to listen to us. We will be talking to NASA and a very special individual all the way from the Jet Propulsion Laboratory in California. Everyone here at Indian Genes is really happy that he has agreed to join us here today and spare his very valuable time as he talks to us. He has a bachelor's in geophysics and space physics from UCLA and a doctorate in planetary science from CALTECH. He has virtually lived the last 8 years of his life on Mars through the Curiosity Rover, and I guess it's safe to say that if anyone knows anything about the conditions out there on Mars, then that is our guest today. So we ask you to now sit back and relax as we virtually fly you to Mars on this Indian Genes exclusive with none other than Ashwin Vasavada, Lead Project Scientist, Curiosity, NASA. Hello Ashwin, and a big welcome to you from Indian Genes. It's an absolute pleasure to have you here, and thank you for taking time out from your busy schedule to talk to us.
And thank you very much for the invitation. It's wonderful to be here, and I look forward to a great discussion and hearing all the questions from everyone out there.
Thanks, Ashwin. A lot of our listeners know you, and for those that don't, why don't you tell us something more about yourself and your role at NASA?
Sure. I'm Ashwin Vasavada. I'm in California now. I work at the NASA Jet Propulsion Laboratory, and I'm a planetary scientist. So I'm a scientist who studies the planets, not just one, but several of them, but focusing on Mars for the past several years. Right now, I'm the project scientist, which is the lead scientist for the NASA Mars Rover Curiosity that launched in 2011 and has been exploring Mars since 2012. So we're just about 8 years on Mars, and we've had a wonderful time exploring, and I get to lead a team of over 500 scientists around the world who work with this rover every day and make discoveries about Mars.
And how did this happen for you at a personal level? What inspired you to be part of the space family, and how early did this start for you? And did you always know that this was what you finally wanted to do?
I've been interested in space since I was pretty young. I think maybe when I was 9 or 10 years old, I was quite interested in seeing pictures of robotic spacecraft that had landed on Mars in the 1970s, and also like the Voyager spacecraft that flew by the outer planets also in that same time, the 70s and 80s. And seeing those pictures when I was growing up just was fascinating to me. It really was this idea that you could send a robot to another world and have a virtual presence there and take pictures and almost have the same view that you would have if you were standing there yourself on the surface of Mars. And I think I just found those images very enticing, and I wanted to be involved in that. I wanted to be able to explore other planets. It was also the time when NASA was flying the space shuttle, so it was always very exciting to see it launch and orbit and then land. But for me, it really wasn't the idea that I wanted to be an astronaut or I wanted to go into space myself. What has driven me since I was young, I think, really is the scientific exploration and just the idea of seeing things for the first time as a human being that no one's ever seen before, and learning things about the planets through the robots that we are able to send into the solar system.
Talking about the Voyager, that's an amazing story on its own, and it just keeps going. I think it's the furthest any spacecraft has ever gone since the 1970 and is still going. Am I right? It's still operating.
Yes, and it is amazing that it's still operating. We build these spacecraft to last a certain amount of time, and we use our best engineering at the time to do that. And the fact that these robots were built in the 1970s with that technology, probably designed I don't know the exact number, but probably designed for 10 years. And now they've lasted upwards of 40 years or 50 years. It's truly amazing. And we still talk to them. It can take a few days by the speed of light for the information to get back between Earth and where Voyager is now. And so it's really stunning that some days I'll walk around the Jet Propulsion Laboratory and there's a display that shows which spacecraft we're talking to in the solar system. And when I see Voyager on that display, it really reminds me that, humans have extended their presence quite far out into the solar system now. And that spacecraft that we built so many years ago is out there at the front of our exploration these days. But I have to imagine that it's far exceeded anyone's expectations for a spacecraft like that in such a harsh environment of space with radiation and very cold temperatures. All the electronics to be able to survive is truly amazing. And fortunately, it used a nuclear power source similar to the one that we have on Curiosity. So those radioactive materials that power these spacecraft do last quite a long time, but even they slowly decay. And so Voyager has been able to stay alive by using only a fraction of the power that it once had when it was first launched.
And since the days of the Viking 1 and 3, the orbiter and Pathfinder, there was a gap of about 17 years, and the missions were put on hold by NASA. What was the reason for this? Was it technological upgrades or something else?
Yeah, planetary science and planetary exploration is a very expensive business. And because of that, it is often subject to, changes in politics in the United States or in any country around the world that does these sorts of things. So, as much as we desire to keep planetary exploration going very aggressively, we are subject to the money that we get from taxpayers in the United States, and also what's important for policymakers at any given time. And we're able to capture the imagination of a lot of the people in Washington, D.C. by grand missions like Viking and Voyager, or the Space Shuttle, or Apollo, even for that matter. And then sometimes you'll see that when those missions are accomplished, the policymakers may lose interest in a way and want to move on to something else with the money that we have. So it's unfortunate, but space exploration does seem to come in waves. We do something, and then there's a gap, and then we're able to come up with another idea that resonates with people in Washington and resonates with the public. And right now, I think we're going through a really exciting time. I'm sure we'll talk about later, where space is once again right at the front of everyone's thinking. And I'm just, very excited to be a part of this now, and I look forward to what's going on in the next few years.
Oh yes, these are very exciting times, and all the more reason we are very happy to be talking to you about this. It would be interesting to know from you, how did Curiosity happen for you? And for you personally, how did this journey begin? What got you started with Curiosity?
Sure. So for me personally, I mentioned how when I was young, I really set out to see how I could become an explorer of the planets. I wanted to be involved in sending these spacecraft missions. And, growing up in California, I knew that all this action was happening in Southern California, where I am now. So I was very fortunate to grow up at least, somewhat near the Jet Propulsion Laboratory. So I went to college in Los Angeles and began working with studying aerospace engineering. I was thinking that aerospace engineering was the way to get involved in these things, and it turned out that even after a few years of college, I realized that I wasn't so much fascinated by the engineering of it, the technical aspects and the design of these spacecraft, But it really was the science that captivated me, the discoveries that these spacecraft made. So it took me a little while in college to find my way to the right field of study. But by the time I graduated from the University of California in Los Angeles, UCLA, I was a Earth and space science major, meaning that I studied the planets, including Earth, and learned how to use spacecraft and other means to make discoveries about them. That led to getting a PhD at the California Institute of Technology in a similar field. And because CALTECH runs the Jet Propulsion Laboratory, it was quite easy to start working with people at JPL and learning how they did their work. So that's how I ended up finding my way. It took me a few years to find my way to the field and how I got involved in it. Now, in terms of Curiosity itself, Curiosity is one step in a long program of missions that NASA has been running since about the 1990s that are exploring Mars. And in about, as we talked about before with Viking, in 1976, we tried to answer one of the most important questions that we could conceive of: is there life outside of Earth? So we designed this very ambitious project to land a spacecraft on the surface of Mars and to carry with it some experiments that could directly detect life. And those experiments were confusing to understand. And, now looking back, perhaps we weren't quite ready with the technology to be able to answer those questions. And it took a few decades for us to get back to Mars and more deliberately, more slowly explore it with a whole fleet of spacecraft starting in the 1990s that first mapped the planet using satellites, then sent landers to specific places to follow up from what we were seeing from space, and progressed through understanding how much water there was on Mars at different times in its history, to then with Curiosity, our goal is to understand whether Mars could support life, whether there was water, whether there's other chemicals and nutrients that life requires, and not actually to detect life, because we're making sure that we build up a complete understanding of Mars before we then again send the next spacecraft like Viking to actually look for life on Mars, because we want to understand Mars as a whole to find those very rare and special places where there might be evidence of that life preserved on the surface of Mars for us to discover. And so, what's exciting is that now, all the way since 1976, we've come back almost full circle to where we've sent these satellites, we've sent these landers and rovers, including Curiosity, and we're right at the brink now of returning for the first time in 50 years almost to a spacecraft that will actually look for evidence of life on Mars with much more information behind it, much more knowledge behind it, and hopefully then a much better chance of success.
Right. So before we get deeper into landers and rovers and any of the missions coming up, can you first tell us the difference between a flyby and a lander?
Sure. The very first spacecraft that JPL ever sent out were flyby missions, which means you launch it from Earth and you aim it at a planet. But then that spacecraft, because of the speed that you need to launch it from Earth to escape the gravitational pull of Earth and the Sun, the spacecraft is going quite fast by the time it actually reaches its target. And this is true for the Voyager missions that took pictures of Jupiter, Saturn, Uranus, Neptune. And it's true even as recent as New Horizons that took those amazing first pictures of Pluto. And those spacecraft just have usually just a few days because they're going so fast. So you're waiting years and years, and then all of a sudden you take all the pictures and gather all the data within just 48 hours as you whiz by the planet. So that's a way to do it. The advantage of doing it that way is that you don't have to include all the capability on that spacecraft to be able to slow down and fire a big rocket engine to then get captured in the gravitational pull of the planet that you're trying to explore. So with Cassini, for example, it's a huge spacecraft. It's sort of the next generation from the Voyager spacecraft. But Cassini had to bring an entire rocket system and fuel with it, so that by the time it got to Saturn, it would not just fly by at enormous speed, but would turn backwards and fire the rocket so that it would slow down enough that Saturn's own gravity would capture it and put the spacecraft into orbit. So it's a big technological step to add that capability. But of course, the advantage there is that once you're in orbit around the planet, you can study it for years, which Cassini was able to do at Saturn. Now, when you're talking about Mars, it's yet another complexity, which is landing. So I think the easiest thing to do technologically is to fly by a planet, which is still, of course, very difficult. The next, more complex thing is to go into orbit around a planet, because then you have to bring a rocket with you, and you have to understand the navigation of how you get captured into an orbit, and then you make that orbit into a circle. It's quite complex. But then when you're talking about landing on Mars, then you have to survive a flight through an atmosphere, coming in at, going multiple kilometers per second, enormous rates of speed, and somehow slow down to fly through that atmosphere without destroying the spacecraft. And then landing on the surface itself is also a very tricky process when there's no landing pads, no safe areas necessarily. You have to figure out how to slow that spacecraft from 5 or 6 kilometers per second to just a few meters per second as you touch down on the surface of Mars.
Oh yes, Cassini was a flyby and did get some of the most amazing pictures of Saturn. We are not in contact with Cassini anymore, right?
No longer, yeah. So it was an extremely successful mission. I believe it was launched in 1997, and it took a few years to get to Saturn. On the way by, it did some investigation of Jupiter, which I was involved in, and that was really wonderful to be part of a flyby mission like that. Because all the excitement happens within just a few hours, and then it reached Saturn and got into orbit around Saturn. It released a probe that was supplied by the European Space Agency, and that probe descended into the atmosphere of Titan, a moon of Saturn. And then Cassini stayed in orbit for several years, all the way until 2017, when, as it was running out of fuel, it was deliberately sent into the atmosphere of Saturn so that we would be sure that the spacecraft would never crash into moons like Titan or Enceladus, another moon of Saturn, both of which may have the possibility of life. So in order to be good citizens and keep the solar system clean of our own garbage, we deliberately sent Cassini into Saturn so that it would burn up and not cause a problem for any of these places that may actually have ancient life.
Oh, that is such an amazing detail and story. I'm not sure how many of us were aware of that, but now that we are, it does address the questions about our responsibility and values as we move forward into these missions, right? Now, prior to Curiosity, there was Odyssey, there was Spirit and Opportunity. How did these missions tie into Curiosity's projects, and what were you able to take forward? Because the Curiosity design is stunning. It's nothing like we've seen before with the cameras and the lasers.
Sure. The Mars program 2.0, you could call it, the one that started in the 1990s after the gap after Viking, was designed very strategically. It was designed to last multiple decades and to very deliberately and carefully reapproach this question of whether life ever existed on Mars, or maybe even if it exists today. And it was built on this realization that when we tried in 1976, we may not have understood Mars well enough to know how to ask that question and where to look on Mars to ask that question. So this Mars program 2.0 I think it started around 1999, was designed to first send orbiters to map the entire planet, understand its topography, understand the different ages of various places on the surface, whether they dated from the early solar system or whether they were formed more recently, to understand whether certain terrains were volcanic terrains, certain terrains were maybe formed, very excitingly, from rivers or lakes. And that's following up on discoveries also from the 1970s, where we realized that Mars actually does have lots of evidence for ancient liquid water. There's riverbeds on Mars. There's craters that were once filled with water. So we wanted to map all that out and build a picture of ancient Mars from those satellite maps, so that we could find, the handful of places on Mars where we could send a spacecraft to the surface and hopefully encounter one of those ancient places that once maybe was a crater filled with a lake, or maybe was a riverbed. And those would be the kind of places where you might hope to find evidence of any life that took advantage of that water billions of years ago. So we first sent spacecraft like the Mars Global Surveyor, which, all the spacecraft, of course, have cameras. That's one of the ways that we bring this information to our human senses in a very straightforward way. But we also mapped the gravity of Mars, understood its sort of internal structure, which tells us about its history. We mapped the temperatures of Mars. We learn about the environment, and temperature data can also actually reveal things like whether surfaces are volcanic or whether they're full of sand, or even in some cases what minerals are on the surface. We also sent the Odyssey orbiter, which is still going today. It's the oldest satellite that we have at Mars. And this spacecraft also was able to, of course, have cameras, but map the planet for its chemistry. That's one of the things that Odyssey was able to do, and temperatures as well. One of the really wonderful missions that has informed our understanding about Mars in a great way was one that we launched. I think it got to Mars in about 2006. It's called the Mars Reconnaissance Orbiter. And even the title kind of tells you what it's about. It's a reconnaissance mission. We're sending this spacecraft to explore Mars for us and do reconnaissance so that we can follow it up with missions like Curiosity. And Mars Reconnaissance Orbiter carried the biggest camera and telescope that we've, I think, ever sent to another planet. So we're able to take these extremely high-resolution pictures of the surface of Mars from space. And that allowed us to understand potential places where we could send landers and rovers very well through these very high-res pictures, but also to measure, to help understand whether there were safe landing places. So with very high-res pictures and using some stereo, some 3D pictures, we could figure out how rough the surface was and whether a spacecraft could land there successfully. So all these orbiters were designed to help us understand the planet and actually help us understand it from a technical point too, so that we'd be ready to successfully land a spacecraft later. As we were sending that series of orbiters, we started also sending a series of rovers and progressively building up our technology to do that. So even before this next era of the Mars program, we did send a very small rover, the Sojourner rover, on a mission called Mars Pathfinder, which was the first time we ever drove a robot on another planet. And it's a 6-wheel rover with a suspension system that was designed specifically for it at JPL. And it was about, not much bigger than the size of a computer monitor, that sort of size. And yet that design is something that now we've retained and built up to bigger and bigger rovers. So all the rovers that JPL have built since then have used that same 6-wheel design and suspension system, which is very good at driving over rocky terrains. We followed up Pathfinder, which just lasted for about 80 days and was really just a demonstration of technology, our ability to drive on another planet. We followed that up with a twin set of missions called Spirit and Opportunity, which are rovers that are much smaller than a car, but quite a bit bigger than the Mars Pathfinder was. And these rovers had a specific goal, which was to follow up some of the measurements that we took from satellites and go to places where we think there once was liquid water on the surface. So, Spirit went to a crater that was thought to have once been filled with a lake, and Opportunity went to an area where there's a lot of a specific mineral called hematite, which is an iron mineral that turns into hematite when it interacts with water. It's kind of like rust. And so each of those missions was sent to follow up, and with the idea of proving to us that water actually was present for long periods of time on ancient Mars. Again, with the goal in the future of understanding whether life existed, but taking just one piece of that at the time to understand the question of water itself. And Spirit and Opportunity were wonderful missions. They taught us so much about Mars, and they each did end up finding evidence that water existed for long periods of time, both sometimes in the way that we thought they would, but actually for each of those missions, they found water in ways that we were not expecting them to. And so it just showed us also that, our understanding of Mars is still incomplete.
Oh, yes. Opportunity in particular went way beyond and was continuing till about 2008.
Yeah, that's right. And we build all these spacecraft to last. Let me put it this way. Every time we build a spacecraft, from Voyager, Viking, Spirit, Opportunity, Curiosity, we always have a specific mission in mind for it. And that mission is, of course, very carefully planned out in advance, whether it would last, and it describes like where the spacecraft's going to go, what it's going to do, how long it will take to get that done. And in the case of Spirit and Opportunity, these were really, after Pathfinder, the first time we'd ever sent scientific robots, with wheels, rovers, to another planet. And so the thought was, we may not know how to do that very well, so we'll give them a mission that lasts about 6 months. And because we're not sure how long they'll survive, we'll make sure that everything that we need them to do will happen in about 6 months. And we call that the prime mission. And any time beyond the prime mission is wonderful, but it's not time that we count on, because so many things can go wrong. And Spirit ended up lasting about 6 years, maybe. So much longer than 6 months. But Opportunity just blew us all away, where it lasted, I think, about 14, 15 years. After being designed for 6 months. So there's if you'll permit me, there's another interesting aspect to all this, which is the story of like how these spacecraft are powered. So spacecraft like Spirit and Opportunity have solar panels. And at the time when we built Spirit and Opportunity, the thought was that one of the reasons that we may only have them for 6 months is because with solar panels, they may get covered up with dust and the power will diminish. And on a dry planet like Mars, you don't really have, windshield wipers and fluids to clean the panels. So the thought was, that may be what limits the life of these missions. After 6 months, there'll be so much dust on the solar panels that they'll stop working. When Curiosity was built, we decided we'll get around that problem by having a nuclear power source, having a power system like Viking and Voyager, which used radioactive material to last for many, many years without worrying about dust collecting on solar panels. Now, the ironic twist in all this is that unexpectedly, the strength and the amount of wind on Mars was able to clean the solar panels of Spirit and Opportunity. And because they use what we now call renewable energy, Spirit and Opportunity were able to keep going for years and years and years with the solar panels. It was completely unexpected. Whereas Curiosity, ironically, because it has a nuclear power source, which is immune from dust but degrades as the radioactive material decays, we have a very fixed, limited life. We know that 5 or 6 years from now, we're going to run out of power and there's nothing we can do about it. So it just shows, how things can, even with the best engineers in the world, you don't really know how to predict the future. And solar panels ended up being the way to have spacecraft last a very long time, whereas nuclear power source ended up being a way to have a fixed, limit to your mission.
It's amazing that you would have to go through both these missions to figure it out. And I think there's no other way of finding it out.
Yes, I mean that's the advantage. And that's what's wonderful about space exploration is it's just been a continuous learning experience since the 1950s and 60s, where every mission teaches you so much about and it gives you more engineering challenges to figure out, and it gives you scientific questions to answer. And part of what's so exciting about being in this field is just having to answer those questions and learn from what's before you and pave the way for what's coming in the future.
And getting to Curiosity with its amazing landing maneuver and 17 cameras and laser throws, it just sounds all very science fiction.
It does sound science fiction, but what's wonderful is that it's science fact. It really, and to be honest, it's engineering that we're talking about here. One of the real pleasures of my job is that even though I'm a scientist and I make, what drives me is to make these discoveries about the other planets, I get to work every day with some of the best engineers in the entire world who know how to design these spacecraft and these instruments to allow, me and the other scientists to answer the questions that we have. There's no way you could do anything in space without it being built on the foundation of really incredible engineering and technology. So Curiosity is an example of that. At the time, it was the most sophisticated spacecraft that NASA had ever built, because even though a spacecraft like Cassini was bigger and in a way, more complicated with more instruments than Curiosity has, Cassini did not have to land and it did not have to drive around. So Curiosity at the time, it was taking our biggest achievement at the time, which was building a spacecraft like Cassini, and using, starting with that complexity and then adding the ability to drive around and have a system where you could drill into rocks on another planet and deliver the powder that you drill into laboratories of the quality that you'd find in a university, laboratory, but made small enough to put on a rover. So there's so many aspects of the mission that are just really, to this day, mind-blowing to me in terms of the technology that was required. And we can talk about many of these, individually if you'd like. I'll just kind of run through them quickly for now, though. I mean, we had to have technology to land a 1-ton rover on another planet. We have never done that before. So this very crazy-looking system of landing a spacecraft by flying it down with a rocket jetpack and landing it on its own wheels on the surface of Mars had to be invented in order to allow Curiosity to do its mission. And then, having a rover, Spirit and Opportunity had instruments on a mast, like the cameras. It had instruments on an arm. What we added for Curiosity was having instruments in the rover body itself. So one of the reasons Curiosity is so big is because the entire front part of the rover is made of 2 scientific laboratories, one of which is a mass spectrometer. Another one shines an X-ray beam through rock samples to figure out what minerals are there. And these are very complicated instruments in themselves. And then you have to put them inside of a rover and supply that material with a big drill on the end of an arm, and do that all without ever being able to clean anything or fix anything. You have to design it in such a way that it can be used dozens of times as you sample different rocks and analyze different samples without ever having the ability to go up there and adjust anything like you would do in any system like that on Earth, many, many times. If you're drilling into a rock, that's a hard thing to do on Earth, and so many times you'd want to adjust the drill a little bit and take it out, put it back in, figure out what's going wrong, clean it. You can't really do any of that, especially not with a human. But other things on the rover, the things I mentioned, the landing system and the ability to have this drill and the laboratories were really the biggest challenges for us. The things that you mentioned, the cameras and the laser, were also challenging, but not as much. But they actually are the kind of the fun parts of the mission. We, as humans, we have to have cameras. We just can't imagine sending these spacecraft out without the ability to bring our eyes with us, to these other planets. So Curiosity has really wonderful cameras that take beautiful color pictures, of course, and most of our missions, especially the ones that land, have 3D vision. So we, of course, have two cameras that are spaced apart, kind of like your eyes are. And we have an instrument on top of those cameras, the one that you mentioned that has a laser. This one's called Chem Cam, or chemistry camera. And it's a pretty fascinating concept. You focus a laser by shining it through a telescope, and that telescope can focus the laser beam to a point on a rock about 5 meters away from the rover. And by the time that laser beam reaches the rock and it's focused into a spot that's smaller than 1 millimeter, it vaporizes that rock. It's so much energy, it actually vaporizes the rock, creates a little cloud of plasma, like a spark. And when we look at the color of that spark in great detail with an instrument called a spectrometer that looks at every wavelength of light, and what that allows us to do is see the color of the spark and turn that into an understanding of the chemical elements that are in that rock. So we can look at the chemistry of rocks from several meters away just by shooting this laser at various rocks around the rover. So that allows us to sample a lot more rocks than we could ever have the time to sample if we had to drill every single one of them. So that's the way when we roll up into a new environment with the rover, we first shoot that laser around at various targets. And if something really looks interesting and unexpected to us, maybe that's the one we'll follow up with driving the rover closer to, and then getting the arm and following up with additional measurements.
That's so cool. And getting to the landing, that was something else that needed great levels of precision and being bold as well, I guess. And you had to have a parachute to slow down the descent after its heat shield was protected, and then lower down the rover from a rope with reverse thrust boosters on. And didn't y'all, I'm not sure if y'all used petals for the landing, or was that for another mission?
Yeah, let's maybe quickly cover the system right before Curiosity's, which is the ones with the pedals. I think maybe you're mentioning. So with Spirit and Opportunity, they were smaller vehicles, and what was able to be designed for them is that anytime you're entering another atmosphere from space, whether it's coming back to Earth like the Apollo missions or SpaceX missions, or landing on Mars with an atmosphere, you have to enclose the spacecraft in a capsule, and that capsule has a heat shield on the front of it. And so as you come into that atmosphere, screaming along, going very fast, and you encounter the atmosphere, the spacecraft heats up. That heat shield absorbs and gets rid of all that heat. And then once you're in the atmosphere, you can open up that capsule and let out the spacecraft. And with Spirit and Opportunity, the spacecraft came out, went down to the surface, and as they were approaching the surface and sensed that they were just a few meters above the surface, a whole series of airbags inflated that basically protected the spacecraft in a giant bubble consisting of maybe like a dozen individual airbags. And the whole system, as I'm sure people have seen, famously bounced along the surface of Mars in order to slow it down. And once it came to rest, the airbags deflated, and then the spacecraft, which was enclosed in this triangular pyramid-shaped structure, the petals of that pyramid opened up, and the rover drove out. That was considered the craziest way to land.
Oh, yeah. The first time I saw that, I was wondering, seriously, is this true? This is what actually happened on Mars?
Yeah, I agree. That again, that's one of the really wonderful parts of the job, is to be around these creative engineers who don't, it's sometimes you can't let your preconceived ideas steer you to something that isn't really the right solution. Sometimes you have to think, as we say, think outside the box.
I guess because these airbags bouncing on Mars was just so raw. You'd expect jetpacks and hi-fi stuff, but not bouncing bags. And was this plan A or plan B?
Right. Isn't that amazing? And, it just comes down to what is the best way to land, given the circumstances that Mars has, and what's the most reliable way, what's the safest way. And something like airbags is actually, in a way, a much simpler system than trying to fire a rocket and keeping, the spacecraft stable while you're firing a rocket and all these things. Just letting it bounce in airbags is actually a pretty elegant solution to that problem. Now, with Curiosity, we first studied the idea of airbags, but because Curiosity is about 5 times as massive as the Spirit and Opportunity rovers, it just didn't scale. The airbags would have to be so big that they would have weighed more than the rover itself. So then we tried whether we could land Curiosity on a big platform that would, come down to the surface firing rockets, and then you land a platform and you drive the rover off of it. But
I think the weight being 1 ton would have been an issue, right?
Yes. That's right. I mean, it was the weight of the rover that prevented us from using airbags, because the airbags would have had to be so big. And then, then it was just determined that, like, why would you land an entire platform or enclose the rover in anything? Because you're just then having to bring all that extra weight with you. So the solution that was thought of was, let's land the rover on its own wheels. Let's use the rover's wheels as its landing gear. And then the question became, well, how do you then lower the rover down to the surface? And the idea of this, what we call the sky crane, was invented, where instead of having a platform under the rover or surrounding the rover, you attach something to the top of the rover that has rocket engines and a very small skeleton, lightweight frame that that fires rockets and flies the rover down about the last 2 kilometers of the atmosphere, slowing it down. And then then you had to think of, like, what happens when you actually get near the surface, which was the really amazing part to me, where the rover is actually lowered down from this this rocket jetpack it was wearing for the past 2 kilometers. That all stops, moving forward about 100 feet off the ground, and the rover gets lowered down on a rope and lands on its own wheels while the rockets are still hovering above it. Very similar. It was based a lot on the design of, like, a helicopter that you might see on TV, like lowering down to rescue someone. A helicopter hovers and lowers somebody on a rope to rescue somebody from the ground. That's the idea, except we have to use rockets instead of a helicopter.
And the velocity at which it would have entered meant you would have limited time, I guess, maybe 5 or 6 minutes to get the speed down first before you could do what you just said.
Yes. And while you do have about 7 minutes from the time you enter the atmosphere going at about 6 kilometers per second to then get the speed all the way down to about 1 meter per second when you actually touch down. Another part of the technology of Curiosity's landing that I think is really fascinating is that, as many spacecraft have to do, you're enclosed in a capsule first as you go from space and you enter another atmosphere. And this capsule protects the spacecraft from the initial heat that's generated when you encounter an atmosphere. So there's a heat shield that protects the spacecraft, and you're going at an enormous rate of speed, 6 kilometers per second. Once Curiosity entered the atmosphere, though, one thing that I think is really fascinating is that capsule for Curiosity was actually turned into a wing, like an aircraft wing, by changing the angle of attack, the direction that capsule is pointed, slightly pitching it up a little bit, it was able to generate some lift and help slow Curiosity down, even while it was still enclosed in this capsule. So we actually flew the spacecraft through the upper atmosphere of Mars on a series of banking turns that slowed the spacecraft down and generated enough lift to keep it from getting any closer to the surface. So it went for about 100 kilometers of distance, flying basically at a level height in the atmosphere, flying like a wing. And only then did it slow down enough where it kind of pitched over, started going more directly down toward the surface, and then a parachute came out and slowed it down even further. Once that parachute slowed it down, the parachute was cut off, and then finally the capsule opened up, and the rover itself was released with this rocket jetpack on it that was designed to fly the rover in a powered way with rockets firing down the last 2 kilometers from the surface. So this long series of events going from the heat shield entering the atmosphere, flying it like a wing for 100 kilometers of distance, and then using a parachute to slow it down, and then this rocket jetpack, and lowering the rover down at the last 100 feet or so down to the surface, all was required to safely land Curiosity. And of course, we can't do anything on Earth while this is happening because we're so far away that the signals take several minutes, 7 minutes in the case of Curiosity, to get from Mars to Earth. So all this is pre-programmed on board the rover, and the rover has to deploy all these systems and time everything perfectly itself without any help from us.
Absolutely stunning. Really stunning. And all through this time, when or how is altitude measured? As I think we're talking about time here, right? But when does the rover know how far it is from ground?
Yeah, some things are timed based on our best understanding from simulations of how long things would take. Other things are directly sensed. So the spacecraft on board has accelerometers, so it can actually sense the gravitational pull of the planet. It can sense the thickness of the atmosphere that it's encountering by how much it's being decelerated by the atmosphere itself. So that helps it understand how deep it is in the atmosphere based on how much pressure it's getting from the atmosphere as it's flying, as it's descending. Once the heat shield comes off, though, and the rover is exposed to the air of the planet, there was a radar that was built into the jetpack that the rover's wearing. Part of that, which includes the rockets that fired, part of it also is a radar system that then bounced radio waves off the surface of Mars to very precisely measure the altitude. So in that last 2 kilometers, as it's descending and firing rockets, it used that radar the entire time to very accurately measure its distance above Mars, figure out when it was in that very final stage where it could lower the rover down on the ropes. And then once the rover sensed the touchdown, those ropes were cut and the jetpack then flew off and crashed 500 meters away. And then the rover was left on the surface of Mars.
Considering the atmosphere on Mars is about 80 to 90 times thinner than that on Earth, the speed on its final stage, would you have calculated that as, I'm not sure, there's no other way you could test those conditions here on Earth?
It's true. I mean, there's certain things we can test in pieces on Earth. We can put a parachute into a wind tunnel and simulate the forces it would have in the Mars environment. We can test the radar by itself. The thing we can't ever do on Earth is test the entire system in a complete test run, because there's nowhere on Earth that has the thin atmosphere and the low gravity that Mars has. So every piece of that landing system was tested independently, and then the entire system was tested virtually through computer simulations. But the first time it ever actually performed all of its steps was when it actually was landing on Mars. And the ability we have to simulate it is limited by our incomplete understanding of Mars itself. So as we were designing this whole landing system, one of my jobs was to give the engineers a sense of what the Martian atmosphere was like. What was its thickness? How fast were the winds blowing? What were the temperatures? At what level were the winds blowing, and in what direction were they blowing? And all these things are known to some level, but not very precisely. So the engineering of that landing system had to be designed to be surprised as well. It had to be resilient enough to encounter winds blowing in the opposite direction from what was expected, or the atmospheric pressure to be much lower or much higher than what was expected, and respond to that safely. So that's the other challenge. Not only is it hard to land on another planet with an atmosphere, but it's even harder when you don't really understand that atmosphere well enough.
And the Mars camera imager, how important was that for landing? It produced some great images.
So for Curiosity, it wasn't used to help land the spacecraft. It was really more of a test of a camera system that could continuously record video during the landing, as well as something that we could use for the public to give everyone around the world a sense of what it's like to land on Mars. So that video that it produced is wonderful for that aspect. But for Perseverance, what Perseverance will do is actually use the camera in real time as the spacecraft is landing to detect whether it's about to reach an area that's maybe a little less safe for landing, and be able to, at the last minute, steer away from that area and land somewhere that's safer.
Speaking about collecting data prior to landing, is MAVEN doing something similar to for the Perseverance landing? Is it preparing this data, or in some way will be supporting the Perseverance mission?
So the spacecraft, the Mars Reconnaissance Orbiter that we talked about earlier, from 2006, is still going now, and it's really the main spacecraft that's used to help all the various landers that have landed since then. So it has this large telescope that takes these very detailed pictures of the surface. It has an instrument that measures the temperatures of the atmosphere so that we can understand the density and temperatures in the atmosphere. And those data sets are the ones that are used to make sure that the spacecraft can land successfully. Other spacecraft like Odyssey and MAVEN do help, but they really aren't designed to produce those data sets. So, the MRO, the Mars Reconnaissance Orbiter, has enabled now, I don't even know how many, but a number of different spacecraft to successfully make it to Mars. So it's been a wonderful mission.
One very important and interesting process you touched on earlier was the laser and how it used to collect rock data. Can we just go back to that, as I think I find it very interesting. I'm sure my listeners would want to hear a little bit more about that as well.
We have a series of steps that we do every time we drive the rover to a new location. We use these images from the Mars Reconnaissance Orbiter even daily as we're doing the mission on the surface, because using these images we can see that over here it looks like there's a unique shape of a mountain range, or over here is maybe where a lake once existed. And so we drive the rover to each of these spots, and then as we drive the rover to a new area, we go through a series of steps where we first image it with our color cameras. And so our geologists can understand and begin to figure out what the area really means. And then we use the laser that you mentioned to do our first chemical sampling of it. So we fire the laser at 3 or 4 or 5 different places. And every time we fire the laser, it shoots out pulses of light. Those pulses of light are focused very finely on a rock with so much energy that they vaporize the rock and cause this little spark. And the color of that spark, we look at with a spectrometer, every wavelength of light in that spark. And the patterns that are emitted by that spark, whether there's more green or more red or more ultraviolet light, actually are diagnostic. They tell you what chemicals and minerals are in that rock. And this is all known from experiments that are done on Earth in laboratories. And it's something that you even learn in a chemistry class in school, where you might take a spoonful of a particular substance and put it in a flame. And the color that is produced while that material is in a flame is related to what substance was put in the flame. And it's the same kind of thing we use on Mars. And so once we shoot those areas and see what is around us, then we'll go to the next step of deploying the arm and putting our next set of instruments on that rock or on that patch of soil to explore it further. And if that data set also is very interesting, only then will we go through the process of taking out the drill and drilling a hole or collecting a scoop of the material and analyzing it in the labs. And we use these steps because drilling and analyzing a sample takes about a month. So we can't do it very often. We have to use all our other instruments first to find the best areas. And only then will we take the month-long experiment to actually study what the material is in detail.
I'm sorry, but I was very distracted in school for other reasons, so I missed that. But to get back to the landing, how did you all come up with the Gale crater as the landing site? Because I guess that would have been a pond in the past, right? And what was so special about this landing site that was selected?
It's a very important question, because you can spend so many years designing the scientific instruments and coming up with this incredible rover and the landing system that's required. But if you don't send it to the right place, you may not discover what you're after. And so we spent several years, about 5 years, going through all the data from the Mars Reconnaissance Orbiter and other orbiters as well, and scouring the surface of Mars for the places that we thought would best tell us whether the conditions that could support life, ever were present on Mars. So obviously we started with water. We looked for places where water was thought to have existed in the past on Mars, whether it's in streams or deltas or lakes or oceans. And we then also looked for places that were quite old, because we think that the first billion years of Mars history was much more promising for life than the present time. So we looked for evidence that told us that these are places that had water about 3.5 billion years ago. The next thing we did was look for places where the geology would capture a record of that evidence. There's not many places on Earth where you can find rocks that are as old as 3.5 billion years old, because other geological processes come and erase that evidence. And on Mars, it's the same thing. You want to find those places that are that old and that actually retain that record that you can read today. And one of the ways that geology can do that is by what's called sedimentary rock, rock that forms as mud and silt and gravel are moved around by water and collect in certain areas and form big stacks of layered rocks. And if these layered rocks survive over time, every layer kind of retains a story of what was happening at the time 3 billion years ago. So we found a site that's very special called Gale Crater, where it once was an empty big crater, a big hole in the ground. But over time, streams of water filled in the bottom of that crater with layers of mud. And those layers are still there today. And so we thought that we could send a rover there, drive up those layers that are now in the shape of a mountain. And as the rover encountered each layer, it would be a record of a different period of time from 3 billion years ago that we could ask with our experiments, was there water here? Was there organic materials, carbon materials? Were there other chemicals that life would require? And overall, did the environment that's captured in this layer of rock represent an environment that could have supported life? And so that's what we've been doing for 8 years, is slowly climbing layer by layer and asking at every layer, does this layer, did it form under conditions that would have also supported life?
And Mount Sharp, which is the biggest mount at the Gale crater there, was that the reason that Curiosity was stuck for some time?
So Curiosity, fortunately, has never been stuck. We've had our share of problems, which I'll talk about in a second. But the Spirit and Opportunity missions each had trouble with getting stuck. And just like we talked about, where we don't quite understand the atmosphere well enough to predict how well we'll land, we also don't understand the surface well enough to predict how safe the rovers will be as they drive. And so with Spirit and Opportunity, we did our best every day to make sure that the rover would drive over safe materials and not get into trouble. But there was one instance with Spirit, for example, where it was driving along on material that looked just like normal sand and gravel without any concern. But just under that layer of sand and gravel, there was a different kind of material that we couldn't see with the cameras because it was buried. But once the wheels dug into that and encountered that, it was very fine material, almost like flour, baking flour, and the wheels could not get any traction, and they just dug deeper and deeper, and it got the Spirit spacecraft stuck. The Opportunity spacecraft also got stuck in thick sand dunes. So, that's what we've been trying to avoid very carefully. As one mission, you learn from the one before you. So far we have not gotten stuck, but we've had, our own issues with our computer has given us problems now and then. Fortunately, we've recovered. And then our wheels have deteriorated more quickly than we hoped. So there's some holes in our wheels from sharp rocks on Mars. But, we've been able to overcome that as well. So, that's what makes these missions exciting, though. You're always overcoming challenges and finding ways to keep going.
And that must be so frustrating for you guys. If something like that happens, just sitting in a car here on Earth and being stuck in the sand is a challenge, in spite of you being in the seat of the car and in control of that spot and the situation. But I can just imagine when something like this is happening on another planet.
It is frustrating, and it's frustrating partly because of this feeling of helplessness, because you are separated by 100 million miles, from the rover. And because of that, you're also limited in your senses. You can only see so much. The first thing you do on Earth is put your head down under the car and maybe dig around the wheels and see what's going on. And with these rovers on Mars, you're really limited in what you can see and what you can sense. And so you just have to be as creative as possible to try to rescue the rover. And one of the things that they did with Spirit was they built an entire simulated environment at JPL, where they took a room at JPL and they filled it with gravel and sand and this very fine flour-like material, and they put an engineering model of rover of Spirit in that environment, and they got it stuck just like the one on Mars was stuck. And then they tested on Earth many different ways of trying to free the rover. And unfortunately with Spirit, they never were able to free it. And that's one of the things that led to its end in 2010. But with Opportunity, they were able to free it from the sand that it got stuck in. And of course, it continued all the way until 2 years ago.
Oh, that's a great insight. I can see it playing out on an upcoming movie as we speak. We were getting to water on Mars now, and Curiosity also found organic molecules preserved in some of the rock samples that could have supported life. So what do you think about the possibility of ancient life once existing there on Mars?
So, as you know, Curiosity's mission was to figure out if the conditions ever were present on Mars that could support life. So we did not have the goal of finding life itself. We had the goal of advancing from the discoveries of water from Spirit and Opportunity and adding everything else that life requires. So was there water? Were there carbon-containing molecules that life could use to build itself from? Were there nutrients for life in the chemistry? Were there any things in the environment that would have prevented life, like toxic substances or too much radiation? So that's what Curiosity was about. And we went to this site, Gale Crater, where we felt strongly that there was evidence of water from 3 billion years ago. And there were all these rock layers to explore, and which represented different periods of Martian history that we could ask those questions. And really, to me, everything that Curiosity has found has only made the case stronger that Mars was a place that would have been very friendly to life if life ever existed 3.5 billion years ago. It turns out that back then Mars was a very, Earth-like planet. There was a thicker atmosphere. It was probably warmer. There was probably rain falling and streams flowing down the side of Gale Crater. These streams, carried mud into the crater, into a lake, and formed these layers that we detected. And within these lakes, there was carbon molecules. There was nitrogen and sulfur and phosphorus and oxygen and all these elements that life requires. It would have been a great place for life to evolve and survive. But at this point, we still don't know whether that actually ever happened. And that's what Perseverance is, of course, designed to figure out. But, the more I look at what we found with Curiosity, it only makes me think more strongly that life was given a wonderful chance to exist on Mars. And it makes me more curious than ever whether life ever was able to take that opportunity.
Well, the obvious next question would be, how confident are we that there is no life there currently?
So we are quite confident that there's nothing obvious.
I was hoping you'd give me another answer.
Yeah, right. It's disappointing in some ways, but not completely. And here's why. So we do believe that the window for life on Mars probably was not that long. It probably was just a few 100 million years in its early history, 3 or 4 billion years ago. And in that time, life on Earth never really got beyond a very basic stage. Most of the time in Earth's history, life consisted of only microbes. And it wasn't until, very recent times, hundreds of millions of years ago, where more complex forms of life really took off. So if Mars never got to that phase and life existed in the form of microbes, we likely would not have found it yet, with all the spacecraft that we've sent to Mars. We may have not looked in the right places or brought the right tools in the Viking timeframe. And since then, we haven't directly looked because we've been learning more and more about Mars and where to do this experiment. So, as we talked about at the beginning, we've finally kind of come all the way back to where we were in 1976, but much more informed, much more educated, so that we could go and actually look directly for signs of ancient life. Now, it's extremely hard. If you were to pick up a rock on Earth from 3.5 billion years ago, and we know that Earth was teeming with life back then, you can take that rock into a laboratory and use the best labs on Earth and still have a hard time convincing yourself that you can prove that there was life, evidence of life contained in that old rock. And so how much harder is it to do, when you're sending just a few experiments on a rover to another planet? Microbes living billions of years ago just don't leave very clear fossils behind. Not like a dinosaur that has bones and, a much bigger body. When you're talking about looking for microbes that were living 3 billion years ago, it's very tough to prove that life was there, which is why we took this very careful approach over the last few decades to find the very best places to look. And then also why we're hoping to bring rocks from Mars back to Earth. So once again, we can use the very best laboratories all over the planet to do this very challenging, study to look at these ancient rocks and definitively show whether there was life or not.
Ashwin, you mentioned a very small window for life on Mars. You were talking about that. Did Jupiter have something to do with this, as it did protect the Earth from a lot of early asteroid impacts compared to the impacts that would have happened on Mars?
That may have played some role, and I'm not really an expert on that. I think what's more important for the history of Mars is how the planet evolved relative to Earth. So Earth is a larger planet than Mars, and because it's larger, it has more volume relative to its area. So the larger a planet is, the volume of it is great, is greater than the area, which means it cools off more slowly. So Earth retained a lot more heat later in its history than Mars did. And that's why we still have plate tectonics today and lots of volcanoes going off. Earth is still getting rid of that initial heat that it formed with, and that all its materials inside are creating. Whereas Mars, being a smaller planet, had relatively more area to get rid of that internal heat from its volume, and it cooled off more quickly. So Mars never went through the stage where Earth is now with plate tectonics and releasing all that heat. Its crust cooled and thickened, which led to another consequence, which is kind of fascinating, where once Mars cooled to a certain point, it lost its ability to generate a magnetic field. Earth has, of course, a magnetic field, which is generated from the movement of molten rock underneath the ground. When Mars cooled quickly, it lost its ability to generate its own magnetic field, and therefore led to it lost its ability to protect itself from things like the solar wind, all these particles that are shooting off of the sun, which Earth is shielded from by the virtue of magnetic field. Now, I'm walking through a number of steps here, but stay with me. So you cool the planet quickly, you lose the magnetic field, you lose your ability to shield from the solar wind. So what happens? The solar wind hits the atmosphere directly and begins stripping away the atmosphere. So in maybe the first billion and a half years of Mars history, that thicker atmosphere that allowed all that water to exist in the early part of the history was stripped away. And once the atmosphere became thin, it became cold, and it became hard for water to ever be stable anymore in the form of lakes and rivers or oceans. And so that led to where Mars is today, a very dry planet, a very cold planet, all the water being frozen. And so that really is what limited that window of possibility of life, is the fact that it only had that thicker and wetter atmosphere for a limited amount of time.
What about under the surface? Is there a possibility of life there?
I think it's possible that life could be present even today under the surface. There's a few thoughts, and these are all fairly speculative, but life requires some complex natural chemistry to get started. It's thought that life originated on the surface of Earth, where lots of chemicals were being mixed around, and you ended up with conditions that allowed the complex molecules of life to first form. So it's not clear that life could originate underground, because maybe that variety of chemistry isn't there for life to make use of. But say life started on Mars at the surface, and then once Mars cooled off and froze, it may have had to recede further and further underground to stay with the conditions that were still warm and wet. And so maybe now life is only deep down on Mars, and it's getting deeper as every year goes by, as Mars continues to cool. If that's the case, it would be very hard for us to ever find it, I think, because you'd have to drill quite a deep way down on Mars, so maybe quite a while from now, when we have heavy machinery on Mars, we could find that, which is disappointing, because it could be a place where life could even exist today. But it's also the reason why missions like Curiosity and Perseverance are focusing on past life, when it would have been at the surface.
So are you saying, even today, that there could be some form of life below the surface on Mars? Is that what you're saying? Because that's interesting.
Yes, that is what I'm saying. And unfortunately, hopefully someday someone will know. But in my lifetime, I'm not sure we'll ever get a drill up on Mars that could drill a kilometer below the surface. That we have a long way to go before we can do that.
And Ashwin, if we do plan settlements on Mars, how do we tackle what you explained earlier, the lack of a magnetic field or the effects of solar winds?
Yeah, it would be quite difficult to think about restarting Mars' magnetic field. So we're probably stuck in the situation where the solar wind continues to directly hit Mars' atmosphere, and the radiation makes it, even down to the surface where it can harm astronauts. So part of the challenge in settling, or having a colony on Mars will be to create shelters that protect humans from the radiation from space and from the sun, and protect humans from the thin atmosphere. So, I suspect that, there are ideas, of course, of terraforming Mars, which I think
I was actually coming to that next.
Yeah, but well beyond kind of what we can do. So I think we have to at least start with the idea of enclosed spaces, shelters that create a thicker atmosphere and protect astronauts from all the radiation.
So since we actually got there, why don't you let our listeners know a little bit more about terraforming? I think that's an interesting concept as well.
Sure. I mean, terraforming has been something that's been talked about, especially in science fiction for many years. The idea that you could take a planet like Mars that currently has a thin atmosphere and has only carbon dioxide and a number of other factors that make it impossible for humans to live there now without any protection. And you could turn that planet back into an Earth-like planet. And that's what terraforming generally is. So there's ideas about how maybe you re-thicken the atmosphere of Mars and you remake it into an oxygen atmosphere so we could breathe. And you have vegetation once again all over the surface of Mars. And these are all fascinating ideas that humans, as small as we are, could reshape an entire planet. And theoretically, I think there's no reason why it's impossible. It's just the scale of what would be required is something that, would be unlike anything we've ever done.
It's funny we talk about terraforming another planet when what we are doing here on Earth is just the opposite. But that's a discussion for another episode. Coming back to Curiosity, what is the future now, Ashwin? What do you personally like to see happening from here on with the Curiosity mission?
Fortunately, now after almost 8 years, we've accomplished nearly everything we set out to do. So I feel very good about that, and I want the mission to continue. I think the spacecraft is in excellent health relative to being 8 years old. So I certainly don't want it to end. But if it were to end, I think Curiosity already has an incredible legacy, which I'm very proud of, and represents a lot of incredible work by all the engineers and scientists that we have shown really definitively that Mars was a place that could have supported life. All the conditions were there 3.5 billion years ago. There were lakes that persisted for millions or tens of millions of years. And those lakes had fresh water. It was a kind of water that life can use, not too acidic, not too salty. The water also had other nutrients that life requires: nitrogen and oxygen, phosphorus, sulfur. It also had, very importantly, had indigenous carbon. It had carbon that was formed that comes from the Martian environment. We didn't bring it, we found it there. And those carbon molecules would have served as building blocks of life. In fact, they may even be evidence of life, but with our technology on Curiosity, we can't determine that. So Curiosity already has an incredible legacy, and it did exactly what it was designed to do, which was to show that Mars, to test whether Mars ever was habitable. And we found that the answer was yes. What we hope to do in the next few years, as Curiosity continues climbing the mountain, is that we'll end up reaching a place that we think might represent the end of that habitable era. So the mountain in Gale Crater, Mount Sharp, is a fairly tall mountain. It's 5 kilometers high. So it's the geology that's recorded in that mountain represents a big span of time, hundreds of millions of years. And the lower part of the mountain that we've explored so far we think all formed in a series of lakes that represent habitable environments. But the upper part of the mountain looks to become a lot more salty. There's minerals that are called sulfate minerals that exist there, maybe more acidic and maybe more dry conditions. So once we reach that upper level and we can test whether the conditions really drastically changed, we may be able to say something about the end of the period of Mars when it was most conducive to life. And I think that would be really a wonderful final accomplishment for the mission, which is to have both shown that Mars was much more Earth-like and habitable than we ever could have imagined, and also be able to say, and it lasted, for this particular period of time. And that will set us up for future exploration and looking for signs of life.
One of the Curiosity findings that got me really excited was the presence of active methane in the Mars atmosphere. Where is that coming from? It just throws up more questions.
You said it exactly right. It throws up more questions. Just before Curiosity launched, there were telescopic observations from Earth and observations from a European spacecraft at Mars that hinted at the presence of methane on Mars. And not only methane, but methane that was variable. That was completely unexpected. Methane, based on our understanding of the chemistry of the atmosphere, first of all, just shouldn't be there. It quickly is destroyed. And it shouldn't be varying either, because it's destroyed over a period of about a few hundred years, which means that it should be kind of a very slowly changing amount of methane, which eventually would be lost very quickly in a few hundred years. But these observations showed that it would come and go with the seasons, which of course, throws up a lot of questions about whether it has anything to do with present day life. We were able to quickly add on another sensor to the Curiosity mission, which directly measures methane from the surface of Mars. And we landed Curiosity and we deployed that experiment for the first time. And we basically couldn't detect any methane. So that was our first surprise, that we saw nothing like the levels that were reported from these earlier telescopic observations. After we continued measuring for a number of years and refined our techniques so that we could measure even more sensitively and smaller amounts of methane, all of a sudden we started seeing it. And now that we've been measuring it for 8 years, we've actually seen a repeatable seasonal cycle, just similar to what was predicted by those early observations, but at a much smaller amount. So we see what we're able to measure is that 1 out of every billion molecules in the atmosphere is a methane molecule, and that even that tiny amount varies, and it increases in the summer and decreases in the winter. So it's very intriguing. We think that there could be natural reasons why methane would be produced underground and vary in the way that it does, and we have some explanations that we've proposed for that. But we also cannot exclude anything that has to do with present day life. We simply cannot tell the difference with our payload. But it is important that we're able to show that it's there.
Oh, that's a very interesting discovery. And I think we should be following up a little bit more on that as we get more information. I think that's going to be very interesting. And Ashwin, we've been hearing a lot about the Curiosity summer trip over the last few days. Could you explain what exactly is the purpose behind this summer trip, or give us a little bit of inside information on that?
Yeah, the what we called our summer road trip is it has to do with what we were just talking about in terms of the next steps for Curiosity. We are just about at that transition from the rocks that go from these environments we think where there was a lot of lakes, to these sulfate minerals that are currently just above where the rover is. But before we can reach that transition to the sulfate minerals, we actually have to drive around a huge patch of sand, a big dune field on Mars. And so there's about 2 or 3 months of driving that we have to do before we can even turn and head back directly uphill to the next layer. And so we decided that we're just going to try to drive as fast as we can. So we're kind of calling it our summer road trip while we're doing it, which means that we look a little less carefully at the ground than we used to. We don't stop as much, and we just kind of go as fast as we can because we really want to get to that sulfate-rich area while the mission is still healthy.
And how fast is fast?
Yeah, generally it's extremely slow by the standards we're used to in driving cars around. We drive, at our fastest, we drive up to about 150 meters in a day. So over the span of a couple hours as we drive, we'll get about 150 meters of distance. But more typically, we only drive about 10 or 20 meters per day because we like to stop frequently and look for any changes that are occurring in the chemistry of the rocks, for example. But for this summer road trip, we're telling the engineers, drive as long as you possibly can on any given day. And in the past few weeks, we've had a number of drives that have been at 100 meters each.
Wow, that's interesting. And you have a big launch coming up with Perseverance. How are you involved in that mission, or are you involved in that mission?
So my job as the project scientist for Curiosity is a full-time job plus. So I made a decision to stick with Curiosity. There's a lot of my colleagues who are the right people to be involved with Perseverance, but you really can't do everything. And I've fallen in love with this mission, Curiosity, and still very excited for what it can do in the next few years. So I've decided to stay full-time on this mission. But of course, as a planetary scientist and someone who's part of this exploration of Mars, seeing the next step, the follow-up to Curiosity, about to reach Mars, is extremely exciting. And this is still part of that initial plan that we talked about that started in the late 1990s, where you map the planet and you find these areas to send missions that can look for signs of life. And you start by looking for water, and then you look for conditions of habitability, which we did with Curiosity. And then you send the mission that can actually directly detect signs of ancient life. And that's what Perseverance is. So, it's an extremely exciting time. I mean, we could have in the next 10, 20 years, we might actually have an answer, a definitive, reliable answer about whether life ever existed on the surface of Mars in the ancient past. Perseverance has two chances of finding evidence of that life. One is with its own instruments. So it's going to drive around. It looks a lot like Curiosity, and its mission will be about the same pace as Curiosity, the same kind of driving and sampling. But it has different instruments, and some of those instruments are capable of looking for patterns in the chemistry, patterns in the mineralogy, ways that the rocks have formed that can tell you that life was involved in creating those patterns. So one of the ways you can detect these ancient microbes, because they don't leave fossils behind, is by looking by how they rearrange the chemistry and the mineralogy of rocks. So you have to bring very sophisticated instruments to Mars to do that, but that's what that's what Perseverance has. Now, if that's not enough, if the signs of life are so faint that Perseverance is not capable of finding them, it will collect, either way, it's going to collect samples that it studies and seal them up into tubes and leave those sample tubes on Mars for a future mission to come collect and bring back to Earth. And once we bring those cores of rock that are taken from, again, the best places on Mars that we think might have once had life, we bring those very carefully collected samples back to Earth. We divide them up, send them to laboratories all over the Earth for the most detailed analysis that we can do. And we even save some for the future, for knowing that technology will get better 50 years from now. We can ask the question, is there any evidence of life in these rocks? And I'm not going to predict what we'll find, but I do think we're coming to a moment where we have the chance of either definitively finding life or definitively not finding it. And so this question that we've been asking not only for 50 years since Viking, but really for hundreds of years. As we ask whether there's any life in the solar system besides Earth, we might actually be able to have a good shot of answering very soon.
And what about the NASA helicopter? Because that is really cool and sci-fi. I think
Right.
it could be the future of explorations. And I must say, it looks very science fiction.
It does, and you can think of the helicopter, which I think is called Ingenuity, as being similar to the Sojourner rover that we talked about. This little rover, which was our first time we ever drove a robot around on another planet, and it only lasted for a few months, and it didn't really, wasn't really designed to do a whole lot of science or anything. Its purpose was to just give our engineers the first ability to try it out, to demonstrate that it's possible. And we did that with a rover, and look where it's led. It's led to spirit and opportunity and curiosity and perseverance. And now we're doing it with a helicopter. So this helicopter mission is really a demonstration, just to show that it's possible and to learn from it. And then it's not going to do a whole lot. It's only going to last a couple months. But how exciting will it be to see something fly on another planet, and to think about what it's going to open up now over the next few decades, where maybe we'll stop sending rovers and future missions will be bigger and bigger aircraft, because now you're not limited to just one landing site, but maybe you could explore a lot more of the planet if you have the same kind of payloads that Curiosity does, but on a helicopter, where you could fly 100 kilometers away and then another 100 kilometers away and explore more and more of Mars.
Oh, yes. A Curiosity hybrid with a helicopter would be perfect.
Absolutely. I mean, I think that's the reason you want to try out these different ways of mobility. Is you just want more and more access to Mars. And with rovers, you're limited because there aren't any roads on Mars, and there are going to be places where, as good as they are, rovers just can't drive. But a helicopter allows you to overcome that. Not only, even just within Gale Crater, we could go to a lot more places if we were able to just jump up in the air and move to a different site and not have to drive over a big obstacle. But then when you think about a mission that could explore Gale Crater and then a year later explore a whole different part of Mars, and then a year later explore yet another different part of Mars, then you're really multiplying what we're going to learn about Mars.
I guess also when we look at these huge space missions, we need to be aware that it takes a lot of effort, passion, commitment. And I think we've been through about 56 missions to Mars so far, out of which just 26 have been successful. So the ones that are successful need to be celebrated and recognized 2 times more than what we are actually doing.
I like that. That's a very good way of putting it. We're fortunately learning a lot more about how to land on Mars. It's definitely not routine, but it's becoming. We're getting better at it, and it's becoming more safe and more reliable. And it's, sometimes the analogy is made with when humans first started flying, where, probably in the early 1900s, when people were flying aircraft in the early days, at least half of those flights ended in crashes as well. And same with when we first started launching rockets. And then when you're talking about landing on Mars, you always go through the same pattern where at first there's a lot of trial and error and failure, but then hopefully, as technology progresses and understanding increases, it becomes more routine and you can expand to doing other things. So it's still a risky business, and there's no guarantee that Perseverance will be successful. But we hope that we're getting to the point where we're learning how to make these systems more reliable and really increase the chance of success.
Would you agree with Elon Musk when he says that within the next 100 years, we would have 1 million people traveling to Mars?
I think I would say that it relies on someone who's as visionary as Elon Musk is. I think without that kind of visionary leadership, it won't happen. But I really respect his vision for the future and what he's trying to accomplish. And I have learned that you should never underestimate him and what he can accomplish. So if he's around and he can find people that can follow him with his same vision and enthusiasm, then maybe that'll happen.
Colonies on Mars is a very popular subject, and we've been getting a lot of questions about that as well. But I think this is a good time to get into what a lot of listeners have been asking us. We started a campaign on our Instagram page asking for our listeners to send in questions. We promised that we would select the top 3 questions from there and ask them to you on this show. But I would like to let our listeners know that we are really thankful to Ashwin because he's agreed to, in fact, address and answer all the questions that have come in. If for some reason your question has not featured on this episode, rest assured, we will be taking this up on our next episode that would be releasing in about a month. So once again, Ashwin, thank you very much for agreeing to take all these questions, and I'm sure our listeners are going to love listening to what you have to say about it. So once again, Ashwin, thank you for agreeing to do this.
Sure.
So let me get straight into our first question. This is from Avantika Singla. And the question is, can human life exist above the Venus clouds?
I'd say yes, but it really relies on taking an environment with us to protect us. So I think humans can survive anywhere if we build a environment that allows us to survive. So build a capsule, build a living space, and above the clouds on Venus isn't probably that difficult because it's not an extreme environment per se. It'd be similar to being in like the space station around Earth. Much more challenging would be at the surface of Venus when the atmospheric pressure is about 90 times as high as it is on the surface of Earth. And I don't think we quite understand yet how to build something that would survive even and protect a robot on the surface of Venus, let alone a human. That's we still have a long way to go to protect ourselves in that extreme of environment.
Mm-hmm. And Ethical Gamer wants to know, is it biologically possible to cultivate on Mars?
It is. So what's really interesting is that our exploration of Mars has really shown that the same processes of physics and chemistry really do operate throughout the solar system. The rocks on Mars aren't made of exotic materials. They're made of the same stuff that rocks on Earth are made out of. It's just, some things have been different between Earth and Mars in terms of the amount of water and the composition and thickness of the atmosphere, et cetera, that have allowed the planets to evolve in slightly different ways. But really, the materials that make up the soil around where Curiosity is not that different from what you'd find if you were on a volcanic region of Earth. And so from that sense, you could plant and cultivate material in the soil on Mars, as long as you also accounted for the things that are different, made sure that the plants had the atmospheric density that they need, the amount of water that they need, other nutrients that they need. But there's no reason to think that the actual soil couldn't be a nice place to grow things on Mars.
Right. Our next question here is from Mr. Shubham017, who says that in the coming future of space exploration, what is it going to be all about? Is it going to be space research? Is it going to be search for extraterrestrial life? Or is it going to be space tourism? I guess his question is, what is going to drive the future of space exploration?
Yeah, the best answer probably is all of the above, because we have different motivations as a society for exploring space, and one of them has always been to have a human presence, and not for any scientific reason, but for the same reason that we explore the top of Mount Everest, or we go to the bottom of the ocean, or we go to the moon with humans, is just to extend the presence of humanity out to these places, and to with kind of an adventurous spirit, show that we can do it. So that, I think, will always be there, and that sort of plays into the space tourism aspect too, where companies will exist so that they can provide that experience to other people, so they can extend their human presence to these places. The scientific research part, I sure hope will be there, but that's the one that really requires governments and taxpayers to see that it's important, to understand that it's important to advance science, because there's really no immediate economic benefit to doing scientific research on Mars. There's really no it doesn't help with that human aspect that we talked about. But as with all scientific research, it requires that that societies just deem it important. That one of the things that makes humans human is to learn and continually understand their surroundings. So I really do hope that countries continue to dedicate their resources, to expanding knowledge for the sake of knowledge.
Very true. And our next question is from Jude Menezes and Zep Tupi. And the question is, what is a realistic time frame for us to be expecting human colonies on Mars?
It's a good question. And, I think, again, it depends, unfortunately, on very specific events that come to fruition. For example, Elon Musk again. When you have someone that's that passionate and that enthusiastic, he's making it happen faster than it otherwise would happen. I think eventually, NASA and other countries will get there. It's inevitable that one day I think we'll have humans on planets throughout the solar system. But what Elon Musk and others are doing are speeding up that timetable, just because they're so passionate about it, and they have their own sources of money, for example. So I fully hope that 20 years from now, hopefully even sooner, there will be astronauts on Mars, carried at least by companies like SpaceX, if not NASA itself. Now, colonies is another question. I think that's still sort of up in the air. You have people like Elon Musk who are very passionate about the fact that humans have to expand their presence to these other planets as a natural course of human evolution, or because Earth itself is not going to be capable of holding people forever, and things are changing on Earth, etc. I'm less sure about that myself. I definitely can imagine in my lifetime we'll have scientific outposts on various planets, like we have in Antarctica for now on Earth. Whether we have permanent colonies for non-scientific purposes, just the living and having families, I don't know personally. I mean, I know Elon Musk wants that, but it would be a very difficult life, and I'm not sure really why people would do that when we have this, when Earth is such a wonderful planet for us to live on.
Talking about long term, we have a question here from Jitendra Kochar, who says, what is the long term goal for NASA post 2050?
I'm not sure we know. I think part of what we do as a species is evolve and respond to what we're finding. And so, perhaps if we are able to show that life was on Mars, definitively, in the rocks that Perseverance collects, that may completely change the focus of NASA to looking more closely at Mars, as well as looking at places like Titan and Enceladus, because if life exists on 2 different places in the solar system, then why not 3 and 4, 5? And understanding, the presence of life throughout the solar system will teach us something fundamental about life itself. If life was able to originate on multiple planets and moons in different ways, independent of each other, then think about what that means for the possibility of life throughout the universe. And yet the opposite may also be true. If we never find life on Mars or Titan or Enceladus, and life only exists on Earth, that tells us something fundamental too about the rarity and specialness of life on Earth. So I'm kind of getting off the subject here, but it's discoveries that will change the course of what NASA does, and like we talked about earlier, we were at the precipice of such a major potential discovery in the next 10 or 20 years, which I then think will determine what we do for the next 50 years. But that's really the science. In terms of humans, I think we'll be on a steady course for the next 100 years, I believe, of expanding the human presence out from the moon to Mars, and then maybe even beyond that, with humans going out to explore the outer planets and moons, not just through robots, but actually having humans go out to those places.
Sure. And Rajesh Gupta wants to know the atmospheric pressure on Mars. How does that impact your missions?
It does. You have to design your landing system mostly to accommodate that low pressure. So when you land on the moon, you don't have to build a capsule around the spacecraft. You don't have to worry about it burning up as it lands because there's no atmosphere. You just can land a naked spacecraft and fire rockets and land. On Mars, and let me contrast that with Earth. When spacecraft are coming back from space to Earth, you have to do the opposite. You have to build a big capsule around it with a big heat shield to absorb all that heat. But then once you're in the atmosphere is so thick that a parachute will just slow you down wonderfully and you can gently land on the surface. Mars is right in the middle, where the atmosphere is thick enough that you can easily burn up as you enter, going 6 kilometers per second. But it's not thick enough to really slow you down with a parachute. So you have to have these intricate landing systems like Curiosity that involve parachutes and rockets and airbags and all kinds of things. So the fact that Mars has this thin atmosphere is quite challenging for missions.
Our next question is from Devanshu Mishra, who says, how is NASA handling the issue of increasing levels of space debris with all the private missions that are now going on?
It is a concern. It's not a crisis, but it requires just a lot of care. So you're probably referring to things like SpaceX launching hundreds or thousands of small satellites for broadband connections. As long as we can track all these different satellites, and as long as they're built in ways that are kind of reliable and maybe even have ways of disposing them at the end of their lifetimes, I think we can, control this. What's really dangerous is when you might have spacecraft that we lose control of, or one of the worst things is if a big satellite is destroyed, if it explodes, or if it's shot down by another country and breaks into many, many pieces. That becomes a real hazard to human spacecraft in particular.
And we have a big fan of the Curiosity design here, that is Abhi9, who says, how did you get the idea for the design? I guess he means what inspired the look.
Yeah, it's a good question. And I don't think there was any kind of top-down thinking in the sense of like, we want it to look like this, and so we're going to build it to look like that. It really is a natural evolution evolution is probably a good word. Why do humans look like the way we look? And it's because, we evolved needing long legs, and we evolved wanting a head that's high off the ground and two eyes so that we could have, 3D vision. And in the same way, curiosity sort of evolved to how it looks because of what we needed it to do. We needed it to have 6 wheels to drive over this rocky terrain, kind of a low center of mass. So you have this big wide body, and the wheels are kind of spread out so that it's very stable. And then you put a little mast on it so you can see high above the ground, and you put 2 eyes on it, cameras. And you just end up getting there in the same way that evolution does it for humans. The design fits the function.
And I think a lot of us agree that the look was really cool. I mean, the colors that we used, the camera. There was a movie not so long ago called Wall-E.
Yeah.
That was an inspiration from that particular mission as well as in the Curiosity mission. But as far as the aesthetics go, I think it's just a stunning looking rover.
Yeah, no, I think you're right.
Our next question is from Mokshanga Sai Teja, who says that with the Perseverance mission, you will be collecting a lot of minerals from Mars and sampling that. And would that also be in some way connected to planning for future life on Mars? And is the Perseverance mission one of the first steps towards that goal?
It's not our main focus, but we certainly are part of the evolution of spacecraft that will one day be able to carry humans to Mars. Like, for example, one thing that Curiosity did was learn how to land a 1-ton payload to the surface. Up until Curiosity, we only knew how to land about 150 kilograms. And so we had to invent this entire new way of landing and learn how all that worked from the technology perspective. We then have to go another factor of 10 above that before we can land humans and all the cargo that they would need. So that's one step that Curiosity was able to help NASA with, in just learning more and more how to build heavier and heavier spacecraft. Another thing we more directly did was we have an instrument that measures the radiation on the surface of Mars. And this instrument was brought with us not really because of our main scientific mission, but specifically to measure the radiation to protect future astronauts. So every day we measure how much radiation is coming onto Mars from space and from the sun. And we see how that changes as the solar cycle changes. The sun goes through an 11-year cycle of activity and sometimes has big storms, solar storms that reach Mars, and we can measure those. And we've been able to build up now an understanding of how dangerous it would be for astronauts to be on Mars' surface. And it's not insignificant. The risk of cancer for an astronaut is much higher if they're living on Mars than if they're living on Earth. But what this instrument on Curiosity has been able to show us is how we can shield those astronauts and protect them, and how hard we have to try to do that in order to reduce their health risk.
And we have a young follower, Yash Shinde, who says, what next after Mars? Where do you plan to go? Is it going to be Jupiter, Venus? What is the next planet that we're looking at?
So Venus is an extremely interesting place, but pretty low on the list of where we think there might be life, because Venus started out as being almost a sister planet to Earth. It's very similar in size, very similar to Mars, to Earth in terms of its distance from the sun. But it just is a little closer to the sun. And that caused it to evolve very differently, to where it became dominated by carbon dioxide in its atmosphere, and the pressure in the atmosphere built up to 90 times the pressure of Earth, and the temperature gets extremely hot. So from a scientific standpoint, it's super interesting, but from a life standpoint, not so much. And similar with Mercury and the Moon. So I think what I'm getting at is that there as long as the focus of NASA maintains on understanding the presence of life in the solar system, planets like that are going to be explored, but at a lower level. And where NASA will focus are going to be places like Mars, places like Titan, the moon of Saturn, Enceladus, the moon of Saturn, Europa, the moon of Jupiter, all of which are places like Mars where there may have been life or even could be life today. What's interesting about Enceladus and Europa in particular is that we've discovered over the past 20 years or so that these moons have ice shells, and underneath those ice shells are liquid water oceans. And so, it's pretty obvious probably that when you have a lot of liquid water on a planet, that is immediately a place where you'd like to go understand whether there's any life. And so I think in the next, again, 20, 30, 40 years, we'll probably do a lot of exploring of those places to see if they might be places where life exists today.
Europa and Titan are very interesting, especially when it comes to the possibility of life. I think we need to get a little bit more closer there, and even if there are possibilities of sending missions in the future, those missions are definitely going to be very, very interesting. And our next question is from, let me get this name right, it's va.rsh4951. If we plant trees with the help of artificial water, we can get oxygen after it grows. And since trees have the ability to convert carbon dioxide to oxygen on Mars, since there is more carbon dioxide in the atmosphere, is that a possibility? That's an interesting question.
Yeah, right. No, it's a great idea, and I think it's one that we might be able to use, I think personally, in kind of a limited environment, like within an enclosed shelter. Maybe that's a way of producing oxygen through a natural system of growing plants. There are people who think maybe we want to terraform the entire planet, by growing plants all across Mars. But that I think is much more ambitious, and all the concerns that you raised about how you bring enough water, to those places would come into play. But one day, if humans are living in a big shelter, maybe 100 people are living on Mars in an enclosed space, it would be great, to grow plants not only for food but also for oxygen.
We now have a question from Jay Patel, who asks you, can we use jetpacks while moving around in zero gravity?
Yes, and that's we can use a jet suit to move around in zero gravity and also in Mars gravity, which is about 1/3 on Earth. I think jet rockets are very useful for all kinds of maneuvering, not just with humans, but spacecraft use them all the time. So it's not necessarily a jet suit, but when you see the spacecraft docking with the International Space Station, they're using little jet rockets in zero gravity to move around those spacecraft.
Right. Question here from Priya Virata. Would there be a combination of AI and robots to build bases on Mars?
I think so. I think it would make sense, especially when we're talking about a sustained presence. I believe, that in the next 20 or 30 years, what we'll probably see are, like we did with the moon, we'll see missions go there and then return without permanently staying. That will be the first step, to live on Mars for a few months or maybe a year and then go back. Once we talk about living, semi-permanently on Mars, then we'll need to bring a lot more infrastructure. We'll need to build more bases and more equipment. And certainly, robots could be sent there to begin constructing all the facilities and getting everything ready before the humans arrive.
This one is interesting. Vidhi Patel wants to know, I don't know if you can answer this, will we ever find a wormhole anytime soon? That's beyond my expertise. I don't know the answer, but hope that'd be neat. An interesting question coming to you here from Aditya Chauhan, who says, if humans ever find an intergalactic civilization on Mars or any other planet, how do you think human beings would react?
It's a great question. And it's of course one that a lot of people are fascinated with, because, we have different movies that and books that talk about exactly this subject of how we would even communicate, and show our intentions, hopefully peaceful intentions, if we ever met other intelligent life. And then, of course, how people would react on Earth. I think we'd have to assume it would be pretty mixed. There would be a lot of fear. There'd be a lot of different reactions, and not just, there, of course, there would be a lot of, I think, positive reaction too. Just the wonder of understanding that we're not alone in the universe. But I've got to imagine that initially there would be a lot of fear and concern as well.
Well, we have a few questions here from one of our followers who goes by the name of Happy Saija. And let me read one of the questions. Mars colonization is beginning. Are there any chances in the future that countries and space agencies will collaborate for space exploration? I think that is already happening, right? It
is happening, and it's not only wonderful to see that collaboration, but it's necessary, because as we do more and more ambitious things like colonizing Mars, the cost involved and the technology involved just goes exponentially higher. And it's really something that NASA can't do alone, or any country can't do alone, but it requires countries to collaborate with each other. So even just bringing back the samples of Perseverance from Mars to Earth is going to involve multiple nations. NASA will send, of course, Perseverance to collect the samples and seal them into tubes, but we're currently thinking that other countries will supply the rover that picks up those samples and deliver them to a rocket. NASA will probably supply the rocket that blasts off from the surface of Mars and goes and takes those samples into orbit around Mars. But then again, another country, maybe a European country, or who knows, will collect those samples from Mars orbit and bring them back to Earth. And by sharing the cost and the technology development between different countries, we think is that's the only way we can do something this ambitious.
Okay, we have a question from a mad scientist here who goes by the name of Prahlad. Well, that's the way he's described himself. And the question is, how would we be able to create a magnetic field on Mars?
Yeah, I mean, my vision may be more limited than Elon Musk's, but to me it sounds very difficult to think of doing something that would shield the entire planet with a magnetic field again, because it was originally formed by movements of molten rock underground that are of enormous scale compared to human beings. But it's perhaps we can do it at a more local scale, where we can shield a particular shelter where humans are living from radiation by having a magnetic field.
And now you have a Curiosity Rover fan here. Akash Verma says, can you please reuse the Curiosity Rover, and could that be done?
Yeah, I'd love that too. I'm just glad it's lasted as long as it has, and we think probably at least another few years left. But eventually, the electronics and all the parts that have been subjected to this very harsh environment on Mars with cold temperatures and hot temperatures and radiation wear out. And at some point, the rover will just no longer be able to function. It won't go anywhere. So I think, one of the things that we can look forward to in 30 years, 50 years, is that one day maybe we can go as tourists to Mars and see some of these rovers. We'll build little museums around them and be able to see how humans first were able to reach the surface of Mars in an era that maybe it's become a lot more commonplace.
Great. Our next question here is from Karthik Shetty. And his question is, what are your thoughts on interstellar travel? And when do you think we would be a Type 1 civilization? The current accepted time frame is approximately about 100 years from now for us to be a Type 1 civilization, right?
Okay. Yeah. And that sounds about right. It does take time for technology to develop. And you have to hope that civilization itself remains stable and continues to pursue things like science and technology. So far, in my lifetime, that's been very good. I think we've lived through an enormously amazing era, from 1900 to the present, where we've gone from not even flying planes to having humans about to go out to Mars one day. Let's hope the next 100 years is as aggressive in pursuing things like that.
Right. We just have a couple of questions left, and this one is from Darshav, who wants to know, why is it difficult to land the rover on the North Pole of the Moon? I'm not sure about the North Pole, but would you be able to answer this?
Yeah, I'm not sure. I may not know some particular detail of why he's heard that it's, or they've heard that it's hard. I don't know the answer. I mean, we can land. I believe we can land anywhere on the moon. There's more interest in landing on the southern pole of the moon currently because there's a huge basin called the South Polar Aitken Basin, where a giant impact occurred in the moon's history, and it may have excavated material from deep inside the moon. So by landing near the south pole of the moon, we can explore more about the interior of the moon, even just by landing on the surface. At either the north or south poles, we believe that there's ice, water ice, which was a discovery that's just happened in the past 20 years or so, where because the moon spins vertically with respect to the sun, the sun only hits the poles of the moon at a very shallow angle. It just glances the top of the north and south poles. So any mountains that are at the north or south poles create shadows that may never be sunlit. So there are valleys in between mountains at the north and south poles of the moon that never receive any sunlight. And these places are among the coldest places in the entire solar system. And ice can accumulate there and survive for billions of years. So it's really interesting because that ice may be a record of the solar system's history of billions of years. But also, of course, that ice may represent a resource that astronauts can use. So we're very interested to go to the poles of the moon with astronauts because of their scientific value, but also because there's water there to sustain humans.
Right. I think he's talking about the South Pole and the ISRO mission that just took place.
I see, yep.
So one last question for you here, and this comes to you from Sister Tube. What is the possibility of the Curiosity Rover meeting Perseverance? So are they going to have a meetup sometime soon on Mars?
That'd be really cool. But so far the plans are not to do that. And that's because we get so few chances to explore Mars that we really want to send these rovers to different places. There's so many places on Mars that we would like to explore. So every chance we get to send a new rover, we send it somewhere different. It is interesting, though, because we really did think a lot about where to send Perseverance. As we talked about, Curiosity discovered that Mars was once a habitable place. It had water, it had carbon, it had all those other things. So why not send Perseverance exactly where Curiosity is to have the best chance of collecting samples that may contain evidence of life? It makes a lot of sense. But in the end, we decided not to do that. And instead to send Perseverance to somewhere that is similar to Gale Crater, where Curiosity is, but also would give us the chance to explore a brand new place.
Right, Ashwin. And as we wind down, Curiosity has been around, interacting with us now for nearly 8 years, and it represents an ideal. And over all these years, you must have built some kind of relationship with it, because it's much more than just a rover on Mars now, I guess, for you.
It is. It's our virtual presence on Mars. We feel very connected. There of course is the connection you build with the robot, which is more than you might imagine you'd have a connection with just a machine. But robots have personalities, they have quirks. You learn to live with them every day. And I know that a number of our engineers at JPL, especially with Spirit and Opportunity, when those spacecraft were eventually ended their missions, there was a sense of loss, a sense of like not having this robotic, companion that you've had for so many years. And I'm sure I'll feel the same way with Curiosity. But, also I think I've just, in a way, I've lived the last 8 years of my life partially on Mars. It's been a very common experience for me to wake up in the morning and to see what the weather is on Mars and to look at where the rover is and look at the rocks and plan my next walk around on the surface of Mars through the rover. And so even in that way, I have this connection to being on Mars that is really unique, that we're able to do that.
That's so cool. Just the thought of having 17 eyes on Mars and a laser, just throw it at any rock that passes by if you're having a bad day.
It's true. I mean, I know parts of Mars better than I know my own neighborhood.
Oh, seriously. I can only imagine that, moving around and capturing fresh images with data and with every move, specifically images that no human has ever seen before. You don't know what you're going to see next, right? It's not like you're moving in a vehicle or you're walking around somewhere on Earth where you have a 360 degrees, you know what's coming. But looking at these images coming all the way from Mars, that must be a stunning experience.
It's true, and that's really coming back to the very beginning of our conversation. That is what has really driven me since I was a child, that sense of exploration. And, my first experience with that was not Curiosity, it was with a spacecraft called Galileo, which explored Jupiter. And I was a graduate student at CALTECH and involved in Galileo, and we were just about to arrive at Jupiter for the first time in the whole mission. It hadn't been there yet. And we had planned a number of pictures of Jupiter after the spacecraft arrived, and they were going to come down at, middle of the night. And so I was in the basement of some building at CALTECH. As the images came down in the middle of the night, I looked at them, opened them up on my computer, and saw these pictures of the storms on Jupiter. And I'll never forget, the moment that it just hit me that I'm the only person in the entire Earth that's ever seen these sights before. No one else is awake. No one else is looking at these pictures. And here I'm seeing things, from hundreds of millions of miles away for the first time. And I get to do that, every morning now on Curiosity as well.
Oh, that's truly awesome. And I'm sure the students listening in are really inspired, like you were on that day. And if you had a chance, Ashwin, to speak to them directly, what would your message to them be, our future pioneers? And one, what would you tell them about the values that need to be looked into as they go down this path? And two, how do they prepare technically?
Yeah, it's hard to give advice that works for everyone, but I really do hope that people will just nurture their passion. What drives exploration like this is it's definitely not just something we do for a job, for money, for fame or anything like that. There's a lot of things you can do on Earth to get money or fame. But what drives things like planetary exploration is curiosity. This is why we name this spacecraft like this. It requires curiosity. It requires this passion for understanding the world around us, and the world meaning the universe around us. And it requires, perseverance to solve problems that have never been solved before, that seem impossible. Landing a 1-ton rover on another planet, understanding whether there's microbes that lived 3 billion years ago. There was a time when we had no idea how to do that, but it took creativity and curiosity and perseverance to answer those questions. So one thing is just to never lose that spirit, and if that's what your passion is, nurture it and follow it, and know that it will come with some sacrifice. Of course, I've been very fortunate that, I've never had to sacrifice too much for what I do. But on the other hand, there's lots of other ways to make a lot of money and work less. But what a privilege that I've been able to do what I do, even though it required a lot of hard work and a lot of following my dreams rather than following other things. In terms of preparing, that's when it becomes a very personal thing. You have to find your particular area that you think you can contribute the best in. Fortunately, we need so many different kinds of people to do what we do. Even within science, there's so many different fields of science. Curiosity studies rocks, it studies the atmosphere, it studies life, it studies chemistry, it studies biology, it studies geology, all these different areas. And the engineering side, it's similar. We need, dozens of different kinds of engineers to maintain the robotic systems of the rover, the thermal systems, the electronic systems, the software, the radio communications. So there's so many different fields, and the best thing to do is to find what field really ignites your passion, and then to become as absolutely good as possible at that field, so that when the opportunities arise to work on these very special missions, you're the one that gets selected to contribute to that.
Well, I don't think we need to say anything more here. Ashwin, it's been an absolute delight talking to you, and thank you once again for your time. Wow. We have spent our time well here, Ashwin, listening to you, and from everyone at Indian Genes, once again, would you ever put yourself through this again?
No, it's my pleasure, and it's an important part of my job also. I mean, we need to communicate these things to everyone, especially younger people. So I appreciate that you're doing that, and thank you for having me.